Hi guys, and welcome to another little series of Year 10 science videos. This one's looking at the topic of chemical reactions. This particular one is number 6 on corrosion reactions. Now, don't go looking for 1 to 5 at this point because I've just launched in, because in the next couple of lessons we're going to be focusing on some of the key reactions that are part of this topic. I will put some others up at some point so you can just rebuild some of that prior knowledge if you need to. So corrosion reactions are effectively reactions involving a metal reacting with oxygen in the atmosphere and forming a metal oxide. Probably the simplest example of this is when magnesium burns in oxygen and creates magnesium oxide as a product. This is a white solid powder, which is very different from the solid magnesium that we started with, and at this point now we're trying to make sure that we balance our equations. But this sort of thing happens probably more regularly than we would like it to different types of materials. It's less spectacular than the reaction involving magnesium and oxygen, but nevertheless it does weaken the materials, and also it doesn't look particularly good either. This copper has taken oxygen from the atmosphere. We know copper is a fairly low activity metal, but nonetheless it will still take some oxygen from the atmosphere to form copper oxide, and then may even combine with some carbon dioxide to form copper carbonate. And you would be familiar with this color of powder because we decomposed it just recently. So while all metals corrode, it's iron that's the one that gets most of the publicity because iron corrodes to produce the corrosion product rust. One of the things that happens when different types of metals corrode is some of them produce an oxide layer on the outside which is quite hard and often impermeable to oxygen. And so what that means is that the discoloration on the outside actually protects the metal on the inside from any further corrosion. The problem with iron is iron oxide does not do that. And what happens is that once rust starts in iron, it continues to eat away until the iron is pretty much completely destroyed. And that's why rust is such a big problem. When we look at different types of metals, we find that the corrosion rates are very different. And it's not just the type of metal itself. Zinc is more reactive than iron, and therefore it will corrode more quickly. Gold is less reactive than iron, and it corrodes much more slowly. But the conditions that each of these materials is in can actually affect the rate of corrosion. You can see the real problem with the corrosion of iron in this little picture here, because you can see not only has the metal discolored, so there's been a color change, but also the fact that it's actually, you can see spots where it's just completely broken away. It becomes very brittle. It loses its hardness, so it's very soft and just cracks. And before you know it, the integrity of the structure is completely compromised. So what we need to do is we need to look for ways of preventing or at least reducing the impact of corrosion. And in order to do that, we need to know something about the different types of conditions that are necessary for corrosion to occur. We need oxygen. Often there will be some sort of an electrolyte as well. So usually that's going to mean water, and especially salt water. And this is one of the problems that we have living near the beaches, in that there's often a lot of salt spray around. That gets into our electrical devices, and it means that if you live close to the coastline, you often find that devices like fridges and washing machines and things corrode much more quickly than they do further away. And that's that additional salt water that's effectively in the atmosphere that is speeding up the rate. It's an ideal condition for rusting to occur. So how do we prevent it? Well, there's a couple of different ways, and there's two sort of groups of ways, I guess. The first are physical mechanisms, okay? Ways of just using some sort of a coating or covering or something in order to try and create a barrier between those key factors of oxygen and moisture and the actual metal inside. So one way is by galvanizing. You coat the material in another metal. Zinc is one of the ones that's often used for galvanizing, and zinc also is capable in this case of acting as part of a chemical barrier as well, it's called a sacrificial anode. And we will look at that in a little more detail in just a moment. But galvanizing is not too different to electroplating, but the zinc coating that can be put on the outside of iron or steel has the advantage in that the zinc itself is a more reactive metal, so if it's scratched, it will still preferentially oxidize before the iron. To create a barrier, you can also paint or grease. The problem with this is the reapplication. You'll have to keep reapplying it if you're going to maintain that integrity, because once it gets a scratch or a break in it somewhere, then the rust can start. Electroplating is similar to galvanizing in that we're trying to put a coating on the outside, but this time we do it with electricity. We actually allow a thin layer of metal to actually plate out on top of our desired metal. So if we've got iron, we can perhaps use a tin coating or a copper coating to just coat the outside and create a barrier. Again, one of the problems with this comes when the surfaces are scratched, and we may need to continue to renew these coatings. Two other mechanisms that can be used in corrosion prevention include sacrificial protection, so that's where we use a very active metal like magnesium or zinc, and in combination we can create a small, like a little battery cell effectively. And the point we're most concerned about is the fact that the iron metal as a solid is going to become an iron ion, which sounds silly, and losing 2 electrons. So it's actually the electrons that we don't want it to lose. We want to push these electrons back basically and stick them back onto the iron, keep the iron intact. But because of the activity of iron, it will readily lose these electrons. And so because magnesium over here, is more likely to lose its electrons, it can kind of force them back into the iron and carry out that oxidation step itself. Cathodic protection is another mechanism, and again it's kind of like the process, if you can think about the process of rechargeable batteries. The battery itself has 2 chemicals that will produce an electric current and allow you to run a device, but when that battery gets low, you can actually put electricity into it and it'll rebuild those substances back up again so that the battery can be reused. And that kind of principle also works by reversing the chemical reaction that causes rusting in order that it can rebuild the iron. Well, I hope this has helped understand a little bit about corrosion prevention, and we might actually carry out an experiment to see if you can actually slow down the rate of corrosion. Thanks for watching.